In this video of gamma function 4, we shall study some more problems on gamma function in which mathematical ideas other than those used in usual gamma function problems need to be used. Let us see how to solve such problems. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. In the first problem, we have to prove that gamma n plus half is 1 into 3 into 5 into so and so forth 2n minus 1 upon 2 raised to n into square root of pi. Before we prove this, let us first understand that in the expansion of gamma n plus half, n is a positive integer only. Next, we also have to use property of gamma function that gamma n equals n minus 1 gamma n minus 1. Now we will expand gamma n plus half, which will be, according to this property, n plus half minus 1 into gamma n plus half minus 1, which will be n minus half gamma n minus half, which will be n minus half into, we will expand gamma n minus half as n minus half minus 1 into gamma n minus half minus 1, which will be n minus half into n minus 3 by 2 gamma n minus 3 by 2, so on and so forth. This further will be 2n minus 1 upon 2 into 2n minus 3 upon 2. Now we will see how the expansion of this gamma n minus 3 by 2 is going to end. Say for example n equals 5. This expansion will be 5 2s are 10 minus 1, that is 9 by 2 into 5 2s are 10 minus 3 by 2, that is 7 by 2 into gamma 7 by 2, which further will be 9 by 2 into 7 by 2 into 5 by 2 into 3 by 2 into half into gamma half. So for any positive integer n, the expansion of gamma n minus 3 by 2 is going to end like 5 by 2 into 3 by 2 into half into gamma half. Therefore we write here so and so forth, and the last terms of the expansion 5 by 2, 3 by 2, half, and particularly for this gamma half we write square root pi, about which we have learned in my earlier videos on gamma function. This we write as 2n minus 1 into 2n minus 3 into so and so forth 5 into 3 into 1 into square root pi upon 2 into 2 into 2 into so and so forth n times. So this finally becomes gamma n plus half equals, writing numerator in the reverse order, it will be 1 into 3 into 5 into so and so forth to n minus 1 upon the denominator 2 raised to n into square root pi. And this is what we have to prove here. In the next example, we have to show that integral from 0 to infinity of x raised to m minus 1 cos ax dx equals gamma m upon a raised to m cos m pi by 2. Now in order to convert this integral into gamma function, we will consider e raised to minus iax equals cos ax minus I sin ax. This you can find in my videos on complex number. So x raised to m minus 1 into e raised to minus iax can be written as x raised to m minus 1 cos ax minus I times x raised to m minus 1 into sin ax. Now this is the real part and this is the imaginary part of this complex number, and the integral that we are given to prove is same as this real part of this complex number. So the integral that we have to prove is the real part of this complex number x raised to m minus 1 into e raised to minus iax. So which will be integral from 0 to infinity x raised to m minus 1 into e raised to minus iax dx. Now this integral is in the form of gamma function. So as usual, we will substitute for this iax here. Iax equals t, so that x will be t upon ia. After differentiation, we get dx equals 1 upon ia dt. Now we write this integral I equals integral from 0 to infinity. In place of this x, we put its value t upon ia raised to this m minus 1 into, in place of e raised to minus iax, we write e raised to minus t, because iax is t, into, for this dx, we write the value of dx here 1 upon ia into dt. This further will be integration from 0 to infinity of this t raised to m minus 1 into e raised to minus t into dt upon this ia raised to m minus 1 into this ia. This we will further write as I equals integral from 0 to infinity of e raised to minus t raised to m minus 1 upon I raised to m a raised to m into ia raised to minus 1 into ia dt. Here ia raised to minus 1 into ia will be 1. So the integral becomes I equals 1 upon I raised to m into a raised to m integral from 0 to infinity of e raised to minus t into t raised to m minus 1 dt. This will be 1 upon I raised to m a raised to m, and according to gamma function, this will be gamma m minus 1 plus 1, that is gamma 1. This we write as gamma m upon a raised to m into 1 upon I raised to m. So we have proved this part, and now in order to prove this part, we will make use of this 1 upon I raised to m. According to the concepts of complex number, this iota I can be written as I equals cos pi by 2 plus I sin pi by 2, because cos pi by 2 is 0 and sin pi by 2 is 1. So finally this works out to be I itself. That gives us I raised to m equals cos pi by 2 plus I sin pi by 2 whole raised to m, which again by de Moivre's theorem, which you will find in my videos on complex number, is I raised to m equals cos m pi by 2 plus I sin m pi by 2, and for 1 upon I raised to m it will be cos m pi by 2. This plus sign will become minus I sin m pi by 2. So the given integral from 0 to infinity x raised to m minus 1 cos ax dx will be real part of integration I, which is gamma m upon a raised to m, this cos m pi by 2. So this is how we can show this integral to be this right hand side. We have just proved integration from 0 to infinity of e raised to minus ax x raised to n minus 1 dx equals gamma n upon a raised to n, where a and n are positive numbers. And from this statement we have to deduce two other statements, one of which is integral from 0 to infinity of e raised to minus ax x raised to n minus 1 into cos bx dx equals gamma n upon r raised to n cos n theta. And number 2, integral from 0 to infinity of e raised to minus ax x raised to n minus 1 sin bx dx equals gamma n upon r raised to n sin n theta, where r square equals a square plus b square and theta equals tan inverse of b upon a. Now let us see the difference between the statement that we have proved and the statements we have to prove. The statement that we have proved has a raised to n, whereas in the statements to be proved there is r raised to n. Moreover, there are terms in cos and sine in the integrand of the integral. So because of that, therefore, we shall have to make use of this data given and we have to apply the concept of complex number. So first of all, we will write this integral I by replacing this a by a plus ib and write it as integral from 0 to infinity of e raised to minus a plus ib into x raised to n minus 1 dx, which will be according to this gamma n upon a plus ib raised to n, where a is r cos theta and b is r sin theta. So a plus ib will be r into cos theta plus I sin theta. A plus ib raised to n will be r raised to n into cos theta plus I sin theta raised to n, and 1 upon a plus ib raised to n, which is a plus ib raised to minus n, which will be r raised to minus n cos theta plus I sin theta raised to minus n, which according to de Moivre's theorem will be equal to 1 upon r raised to n into cos n theta minus I sin n theta. So this integral will be, now this integral we rewrite as integral from 0 to infinity of e raised to minus ax into e raised to minus ibx into x raised to n minus 1 dx. Out of this exponential form e raised to minus ibx can be written in the polar form of complex number as cos bx plus I sin bx. Therefore, this integral will become integral from 0 to infinity of e raised to minus ax into cos bx plus I sin bx into x raised to n minus 1 dx equals this gamma n upon, in place of this 1 upon a plus ib raised to n, which is this and whose value we have found over here, we will write it here. That will be gamma n upon r raised to n into cos n theta minus I sin n theta. For better understanding, let us write the last part. Once again, integral from 0 to infinity of e raised to minus ax into cos bx minus I sin bx into x raised to n minus 1 dx equals gamma n upon r raised to n into cos n theta minus I sin n theta. Let us write this in the expanded form. Integral from 0 to infinity of e raised to minus ax into cos bx into x raised to n minus 1 dx minus I times integral from 0 to infinity of e raised to minus ax into sin bx into x raised to n minus 1 dx equals gamma n upon r raised to n cos nx minus I into gamma n upon r raised to n into sin n theta. Now by equating real and imaginary parts, we will get our result. The first result will be, after equating this real part, integral from 0 to infinity of e raised to minus ax cos bx x raised to n minus 1 dx with this real part gamma n upon r raised to n minus 1 cos nx, and number 2, equating this imaginary part integral from 0 to infinity of e raised to minus ax sin bx into x raised to n minus 1 dx equals gamma n upon r raised to n minus 1 sin n theta. There are two writing mistakes which need to be corrected here instead of cos nx there should be cos n theta, and here instead of cos nx there should be cos n theta, and here instead of r raised to n minus 1 there should be r raised to only n, and here instead of r raised to n minus 1 there should be just r raised to n. Next we have to evaluate integral from 0 to infinity of cos of a x raised to 1 by n dx. We will substitute for this ax raised to 1 by n equals t. So x raised to 1 by n will be t upon a. So x will be t raised to n upon a raised to n. After differentiation, dx will be 1 upon a raised to n into n t raised to n minus 1 dt. So this integral turns into I equals integral from 0 to infinity of cos t into, for dx we write 1 upon a raised to n into n t raised to n minus 1 dt. This will be n upon a raised to n integral from 0 to infinity of cos t into t raised to n minus 1 dt. Since there is cos t into t raised to n minus 1, we will make use of exponential form of a complex number e raised to minus it, whose polar form is cos t minus I sin t. So if we write integral from 0 to infinity of e raised to minus it into t raised to n minus 1 dt, then it will be integral from 0 to infinity of, putting in place of e raised to minus it cos t minus I sin t into this t raised to n minus 1 dt. We will get two separate integrals, which will be the first one integral from 0 to infinity of cos t into t raised to n minus 1 dt minus I times integral from 0 to infinity of sin t into t raised to n minus 1 dt. Now this is the real part of this integral, which is same as this integral. So this integral I becomes real part of n by a raised to n integral from 0 to infinity e raised to minus it into t raised to n minus 1 dt. So let us find. Next we have to evaluate integral from 0 to infinity of cos of a x raised to 1 by n dx. We will substitute for this ax raised to 1 by n equals t. So x raised to 1 by n will be t upon a. So x will be t raised to n upon a raised to n. After differentiation, dx will be 1 upon a raised to n into n t raised to n minus 1 dt. Well, we will substitute for this it equals u. So t becomes u by I, and after differentiation dt becomes 1 by I du. Now this integral I becomes real part of n upon a raised to n integral from 0 to infinity of e raised to minus u, putting u for this it into t raised to n minus 1 u raised to n minus 1 upon I raised to n minus 1, and in place of this dt we write this 1 upon I du. This further will be real part of n upon a raised to n integral from 0 to infinity of e raised to minus u into u raised to n minus 1 into 1 upon I raised to n upon I into 1 upon I du. Now this 1 upon I cancels with this 1 upon I, and in the next step we get real part of n upon a raised to n into 1 upon I raised to n, and this integral according to gamma function will be gamma n minus 1 plus 1, that is gamma n, which is real part of 1 upon a raised to n into I raised to n into this n into gamma n will be gamma n plus 1 according to properties of gamma function. Now we have I equals cos pi by 2 plus I sin pi by 2, because as we know cos pi by 2 is 0 and sin pi by 2 is 1. So this works out to be I itself. Therefore 1 upon I will be cos pi by 2 minus I sin pi by 2, which is the polar form of 1 upon I. Now this integral I further becomes I equals real part of this gamma n plus 1 upon this a raised to n, and for this 1 upon I raised to n we will substitute cos n pi by 2 minus I sin n pi by 2. So the value of integral I will be gamma n plus 1 upon a raised to n into this cos n pi by 2. So this will be the value of given integral. Next we have to prove that integral from 0 to infinity of x e raised to minus a minus ib x cos bx dx equals a square minus b square upon a square plus b square whole square, and integral from 0 to infinity of x e raised to minus a minus ib x into sin bx dx equals 2ab upon a square plus b square whole square. If we observe the integrals, we find that these two integrals are similar to gamma function, and since there are cos bx and sin bx in the integrals, we have to make use of concepts of complex number. So as usual, we will start by assuming a minus ib into x equals t, so that x will be t upon a minus ib, and after differentiation dx will be dt upon a minus ib. So the integral from 0 to infinity x into e raised to minus a minus ib into x dx becomes integral from 0 to infinity for this x t upon a minus ib into this e raised to minus t, and for this dx we will use dt upon a minus ib, which will be I equals integral from 0 to infinity e raised to minus t into t upon a minus ib whole square dt, which will be 1 upon a minus ib whole square into integral from 0 to infinity of e raised to minus t into t dt. This will be I equals 1 upon a minus ib whole square, and this according to gamma function will be gamma this 1 plus 1 gamma 2, which is 1 upon a minus ib whole square into gamma 2 is 1 factorial, which is 1. So this will be 1 upon a minus ib whole square. Now this 1 upon a minus ib whole square will be 1 upon a square plus I square b square will be minus b square. I square is minus 1 minus 2ab I. Now for rationalization of this denominator, we will multiply numerator and denominator by the conjugate of this denominator, which will be a square minus b square plus 2ab I upon a square minus b square plus 2ab I. This will be a square minus b square plus 2ab I upon a square minus b square whole square minus 4a square b square, and because of this I square, which is minus 1, this minus will become plus. But in the result we want a square plus b square whole square. Therefore we have to write this denominator in terms of a square plus b square whole square. Now let us see how to write this. Now we have obtained given integral I to be 1 upon a plus ib whole square, which we have obtained a square minus b square plus 2abi upon a square minus b square whole square plus 4a square b square, which further will be, this expansion will be a square square plus b square square minus 2a square b square plus 4a square b square, which will be a square minus b square plus 2ab I upon a square square 4a square b square minus 2a square b square will be plus 2a square b square plus b square square, which will be a square minus b square upon, for this whole thing, a square plus b square whole square plus 2ab I upon, for this whole thing, a square plus b square whole square. This integral I is nothing but integral from 0 to infinity of e raised to minus t into t upon a minus ib whole square dt. Now we will back substitute for this t equals a minus ib into x and write this integral from 0 to infinity of e raised to minus a minus ib into x dx equals integral from 0 to infinity of e raised to minus ax into e raised to ibx dx. This will be integral from 0 to infinity of e raised to minus ax. Now this e raised to ibx is the exponential form of a complex number, which in the polar form can be written as cos bx plus I sin bx into dx. So this integral is split into two parts, integral from 0 to infinity of e raised to minus ax cos bx dx plus into sin bx I dx, which is equal to this whole thing. Now if we equate this real part of the integral with this real part, we will get this first result, and if we equate this imaginary part with this imaginary part, we will get this second result. Friends, if you like this video, please click the like button. Share this video with your classmates. Don't forget to subscribe this channel. Make constructive comments to help improve my videos. See you in the next video. Until then, keep watching Number Collage. Thank you.